Okay, so today is what? Today is the 5th of February 21, and this is lecture 14, right? So let's review where we are again very quickly and where we are going. So we were talking about centroid, and we demonstrated if you have a general area, and what I mean by general area or area of general shape, okay, that is an area given by, described by some functions, or an area that is made of a composite of shapes consisting of some simple geometric shapes. How to find the centroid of that shape, okay? Now we're going to go one step further and introduce the a concept called moment of inertia, or the second moment of an area. Before I get to show you mathematically, let me first give you sort of a background why we need to find moment of inertia. By mistake, we call it moment of inertia, because in statics, we're not dealing with inertia at all, but rather we are dealing with area, and we are talking about second moment of an area. What does that mean? What is the meaning definition of moment? Moment is what? Force times a distance in 2D, right? So you remember, if so those of you who've had statistics or probability, you remember how you find the mean value of a function, or I mean a mean value of a probability, okay? How many of you have had, a lot of you have had probability, right? Or no? Okay, silence, that's okay. But anyway, whether you've had it or not, okay, is this. Moment in a probability theory, okay, the mean value describes the way the average value under this probability curve, okay? And for instance, if you had a probability curve like this, or like this, or probability distribution like this, or like this, they all have the same mean value, in this case, or mean value 0, but they can be of different shapes, right? You know, centroid in of an area is physically means the same. What you're doing when you're evaluating the mean value of this area, which is its centroid, okay? If you look at this area, okay, and this area, okay, they both have the same mean value, the same centroid. However, this area is less scattered, let's say, about y-axis than this one, or for that matter, this area is what? Less scattered about the x-axis than this area. Okay, this is much more scattered about this axis. Each differential areas are further away from the x-axis. So in order to determine how an area is distributed about these axes, that's where the concept of moment of inertia or second moment of an area comes into play. Same as the probability theory. In order to find out whether this shape or this shape of probability density function, okay, the one that it is more scattered about mean has a smaller moment of standard deviation than, larger standard deviation than this one. So if this is 1 and this is curve 2, the standard deviation of 2 is less than the standard deviation of 1. Standard deviation probability shows you how data is scattered about certain mean value. Moment of inertia, or the second moment of an area of a shape, demonstrates how that area is scattered about certain axes. How? To find the mean value for a centroid, what you did was what? You basically had this function, forget about the denominator, is the same for both x and y, but you basically had something like this, right? You were evaluating x bar times dA. So look at this. If you look at these little differential area as a force and this as a distance, this is what? This is the moment of this area about that center, right? We call that the first moment. Why? Because moment of inertia is defined now this way. We call that first moment where you have a force taking the linear distance or vertical distance between that and that point. So is similar to this, right? Now, moment of inertia of Ix is given by this function, or for y is given by this function. And look what we are doing here, okay? You are taking the moment of this area and multiplying it by another distance. So you're taking the moment of the moment. In other words, this is the moment, multiplying it by distance. So you're taking the moment of this quantity, which is the moment. That's why we call that second moment. That's why standard deviation is also the moment of the moment, or the first moment, or the second order moment of this shape. That's where the name comes from. So moment of inertia is nothing by taking the second moment. But what is the significance of that? Why am I talking about this? The reason it is important, the reason I'm discussing this, is for those of you who've done construction work, for instance, you do remember that, you realize that if you have a piece of timber, right, like this, you want to build a deck, you don't put, when people are walking on that, or load is applied, you don't put this cross section like this, but you put it like this. Same area, same centroid, okay? But we say that this timber put this way can handle the load better against bending about this axis, okay? Because when you're finding the moment or the bending of this about this axis, that is the forces that are generated due to this load inside this beam, okay, are calculate, as you see in the next course, strength of material. We want to find the stresses, which are the intensity of the load, distribution of the load inside this structural member. These are reversely proportional to the moment of inertia, or the second moment of an area about this area, about this axis. So if you look at it this way, if this area located like this, its areas far more scattered about this axis than this one. So it has a larger moment of inertia. Therefore, its bending stress would be less. That's why we put those pieces of timber like this. Let me demonstrate that through an example for those of you who haven't had. Let's say I'm looking at this, okay? This is the cross-sectional area, okay? So what I'm saying is, if you put it like this, the cross-section about this axis is less scattered. The area is less scattered. So when you put the load like this, you can see that it bends easier, okay? Whereas if I apply the load this way, that is, I'm putting the area like this, that is more scattered about the same axis, and if you apply the load, it is much harder now to bend this that way, okay? Putting it like this, you cannot bend it as easily as you put it like this. That's the reason you study moment of inertia later on, to see how you can find the stress distribution and which axis will give you a better resistance to bending, okay? Similar to the centroid, when we are dealing with moment of inertia, we also consider two cases. Again, general area and composite areas, okay? So I will start with the general areas as we did with centroid, okay? So, and demonstrate how you can find the moment of inertia or second moment of the area of a shape, okay? So let's consider, for example, something like this. You have an area described by these two functions. This is given as, if this is B or A, this is B, this is BA over X. This function would be B over A squared X squared. You want to find the moment of inertia of this shape about X-axis and about Y-axis. These are the two equations. Now, don't get into the deriving these. You've had those in calculus. Let's start with I of X. I of X is given by this integral. I of Y is described by this integral. So for X, Y squared, for Y, X squared. This is a procedure to find those values. Let's start with IX. Step number one, okay, consider a differential element with sides, meaning the two long sides, parallel to X-axis. So you remember in centroid, you had this equation, X dx, X dA, and you would take dA as a differential element with sides parallel to Y-axis. Here is a direct correlation. You take a differential area for x that its sides are parallel to the axis, x-axis. So if I call this y2, this is y1. So this is dy. So this distance is y, is what would be x2. And this distance would be x that you find from this function, right? So you simply write as a next step the equation for dA, which would be what? Would be x2 minus x1 dy. Once you set that up, okay, write the mathematical expression for x2 and x1 from these functions. What is x2 from here would be what? Would be from this equation, okay, would be a squared y divided by b, okay, for x1, which is this, x from this function would be ay divided by b, right? So dA then would be a squared over b y minus a y over b. So this is dA. You set that up, okay?
Why is the equation
I'm
for
sorry,
x?
wait. No, I confuse you. From here, actually x2 is not that, would be a square root of that, right? So would be a y half b half. Okay, I think I have not waken up yet. I haven't had finished my coffee. Is that what your question was?
I was just gonna ask you like how you got to those, if you could just kind of explain how you got to those two.
Oh, you see, you have been given a function, right? So y is b over a squared x squared. You want to find x in terms of y, right? That's what this is. This is the x value from this function, right? So x2 is what? A squared divided b times y, right? So this x would be a over this. You see that?
Yeah, that makes
Any
sense.
x, any x along this function is evaluated from here in terms of y. You want x in terms of y, right? And that's all I did. So now you substitute this into this equation, okay? So Ix would be y squared integral y squared times a b half y half minus ay over b. The bound of integration dy varies from 0 all the way to b, okay? So let's simplify this a bit. I take a over b to the power half out, so I can write this like this to make it a little bit simpler to integrate. So I get y squared times now y half over, okay, I have y squared over, um, b half minus y over b, okay? I'm sorry, I would simplify that. That will be, I take a over b half out. So I would have y, actually, let me leave it like that for the time being. Okay, I do it here. So if you multiply these, and take that out, a over b to the 1/2 from 0 to b, you will have, okay, y to the 5 half minus y 3 over b half dy. So multiplied y squared, so y to the 5 half, and then I had taken b over 1 half out, so this goes out and you have this. So simplify that, okay? So perform the integration, you get a over b half, 2/7 of y 7 half minus 1/4 of y 4 over b half, evaluate from 0 to b. So if you substitute that, you get a over b to the 1 half, 2/7 b 7 half minus 1/4 of b4 over b half. These simplify, you get a b cubed times 2 half minus 1/4, and that gives you I sub x is equal to 1 over 28 of a b cubed. Okay? So the moment of this area, second moment of this area, about x-axis is given by this function. That means this indicates how this area is scattered about that axis. Now, if I go about finding the distribution or moment of that area about that y-axis, let's see how much that will be, okay? Any questions? No? Okay. So let's do that. Let's now find the moment of that area, second moment of that area about y-axis. This is the formula you use, x squared dA. So now I want to find the same shape, moment of this area, y was b over a squared x squared, y is b over ax, okay? About y-axis, about this axis. So procedure is the same. You set up now, though, a differential area, this time with sides parallel to y-axis. Okay? That is, this is the differential area I'm going to consider. This is dx. What is the length of this side of this little rectangle? This is going to be y that I'm finding from here. That is, this is y2. This is y1. So dA, I set that up as this next step, would be y1 minus y2 dx, or what is y1 from this curve would be b over ax. What is y2 from this curve is b over a squared x squared dx. So once I find that, now I will put it in this equation. Integral of x squared times dA, which is b over ax minus b over a squared x2 dx, bound of integral. Dx varies from 0 to a, so you just simply evaluate that integral. So I will take b over a, factor that out. So 0 to a, x cubed minus 1 x squared, x fourth, I would multiply that, over a dx. Okay, so integration is simple, would be 1/4 of x4 minus 1/5 of x5 over a from 0 to a. So substitute for a, you just get b over a, 1/4 of a to the fourth minus 1/5 of also a to the fourth. Okay, and that will give you, if you simplify this, that will give you b over a, or actually I would further simplify that because this a and these would cancel out. So that gives you b a cubed times 1/4 minus 1/5. So IY comes out to be BA cubed over 20. So this is IY, okay? And IX was 1/28 of AB cubed, okay? So depending on which one is larger, that means you have a larger moment of inertia about that axis, and that is the axis you consider if this is a piece of lumber and you want to put it against the load. So if that is a piece of lumber with this cross section, something like this, okay, you want to know if it is going to be stronger this way or stronger this way. Let's just give it some number. Let's say A is equal to 1, B is equal to 2. Okay, so if that's the case, then you have IY, okay, A is 1, so would be 1/10, and IX would be, okay, this is 2, so it would be 2/7. That would be I. So obviously this is larger, right? So it is going to be stronger if you consider just put this timber in this direction. So loads would be acting like this. So bending would be taking place about the x-axis. Okay. So as you can see, the second moment of an area is a quantity that we will find in order to, as you will see later on, to determine which axis you should consider for bending or subject that piece of a structure to bending. Now, I have another example. This is actually a better one, okay? If you look at, this is the cross section. This is, right? So I can put it like this. So the bending would be much easier than if I, in other words, if I put the loads this way, okay, about this axis, bending takes place much easier than if you put it like this. There's no way you can bend this as simply as you did that way, okay? So that's what the meaning of the second moment of an area is all about, okay? I have a few other examples I can, with the limited tools that we have here. Look at this, the cross section of this deck of cards, right? So if you look at it this way, if I want, this is the bending axis. So is this area has a larger moment of inertia about this axis or this one? This one, because it is more scattered. If you find a moment of inertia of this shape about this axis, it is much larger than the moment of inertia of this area about the same axis. So I consider the area to be this way when I put these loads and try to just bend these deck of cards like this. Whereas if I put it like this would be the loads. As you can see, it bends so easily. But you don't need to worry about that. That's what you see in the second course, Strength of Material. Just want to show you the physical meaning of this. So, moment to conclusions that we derive from here, okay, is that the moment of inertia, okay, depends on the axis about which you find that, okay? All right. We are mainly interested, let's say, in case of moment of inertia, like centroid, we are mainly interested in composite shapes, right? Because for the most parts, in structural mechanical systems, the kind of structural components you consider, they have cross-sectional areas that are made of, if they are not just simply made of a simple geometric shape, circular or triangular or elliptical, they would be of shapes that are basically of composite form. Okay, so the next topic that I want to discuss would be this. However, before doing that, I need to introduce, in fact, a very important review, a very important concept that you have had in calculus, okay? And that is called parallel axis theorem. Does any of you remember that, right? Do you remember that? If you don't, that's okay. This is the concept of the parallel axis theorem. If you had an area, let's say I have a shape like this, I do know what is the moment of inertia of this shape about its centroidal axis, that is an axis that is going through the centroid of this shape. So let's say this is a structural element, okay? And I want to know, okay, I have the moment of inertia, I know how it's gonna, what is its value about this axis, but I have restrictions. I have to use this in the same orientation. But I can consider the axis of bending to be something that is parallel to this axis. Let me give you an example. If those of, I don't know how many of you are aerospace engineers, if you look inside the wing of an airplane, the components that goes into that, there's a component called, they call them stringers. The stringers are sort of, for lack of a better word, I-beams like this. You have these sort of solid tubes connected with a very thin layer of a metal, okay? And you have a bunch of these inside the wing, okay? Is a lightweight structure. So the load obviously applies like this, okay? So you have to put these in these sort of areas so that you want the bending about this axis. But you can find the moment of inertia of, let's say, this shape about this centroidal axis of this shape, but you want to know, okay, if you put these further apart, obviously the area is further from this axis of bending, so it generates more moment of inertia. But if I have the moment of inertia about this for this shape, how do I find the moment of inertia about that shape for that shape? Parallel axis theorem gives you the tool that once you have the moment of inertia of this shape about its centroidal axis, you don't have to redo the calculations for a shape that is similar, but you are going to find the moment of inertia about an axis that is parallel to it, okay? So this is the theorem. If you want to find, if you have the moment of inertia here, about x-axis, which is the centroidal axis of this shape, but for something like that reason, you want to find the moment of inertia of that shape about an axis that is parallel to it. You see here, you have the moment of inertia of this, about this axis. You have that. But you want to know, if I put this shape at a distance from an axis that is parallel to this, okay? What is the moment of inertia of the same shape about this axis? This is what you do. As long as you have the vertical distance between these two axes and you have the moment of inertia of this shape about its centroidal axis, you can find the moment of inertia about an axis that is parallel to it by just simply writing that value and add to it this quantity. Take the area of this shape, multiply that by the square of the vertical distance between these two axes, and you find the moment of inertia about this new axis. This comes quite handy, and let me show you through an example. Let's say,
Would you mind leaving that up for just another second?
sure.
Thank you. Okay, thank you.
Sure. So let me do an example. Let's say you have a rectangle, okay, width b and height h. So this is h over 2, this is h over 2. So these two are the centroidal axes of this shape. This is centroid. So this is the x centroid, this is y centroid, okay? Let's first find the moment of inertia of this shape about its x centroidal axis. I want to find Ix, so that'll be what? Y squared dA. So you need to set up dA, and dA, it has parallel to the x-axis. So this is dy, but since this is constant, dA would be simply what? B times dy. So I of x would be this integral of x squared b dy, and dy goes from here to here, but since this is symmetric with respect to this axis, I take half of this integral, so I consider the bound from 0 to h over 2 and multiply that by 2. It would give me the same value, all right? So let's evaluate this. So this is 2 integral from 0 to h over 2 y squared b dy, okay? So this gives me 2, 0. I take b out, h over 2 of y squared dy, or 2b, okay? 1/3 of y cubed from 0 to h over 2. Okay. So if you calculate this, you get 2b 1/3 of what? H over 8. So this would give me 112 cubed, I'm sorry, 112 of BH cubed. So this is the X moment of inertia about the x-axis. Now, if I want to find the moment of inertia now about this axis, about the base of this rectangle, I don't have to repeat that procedure. You can do that and you're more than welcome to, okay? So now if you want to do that, you have the y again, you need to set up the integral going from 0 to h and so on and so forth. But what I say is that I, about x-axis, instead of going that route, I just take the moment of inertia about centroidal axis, okay, and add to it the area of this shape times the square of the vertical distance between these two, which is h over 2 squared. Okay? If you do that, this would be bh cubed over 8 over 4. Okay? If you do that. And you see that if you add these up, you get 1/3 of bh cubed. So you could quickly find the moment of inertia about another axis that is parallel to it. Now, this is a very powerful tool that we will employ when it comes to finding the moment of inertia of composite shapes. But before I go there, let me refer you to a table similar to the table for the centroid in the back of your book. If you look at the back of your book, you see that the moment of inertia for simple shapes are tabulated, okay? And this is in fact what I just did for this rectangle. Moment of inertia about x prime, which is the centroidal axis, is 112 bhq. About this is 1/3 of bhq, and y axis and y prime axis as well. And you see all of these, okay? We need these tables. We will use them extensively when we get to doing the moment of inertia of a general shape. And I'm going to start with this example. We may not be able to finish it, but I will at least show you, you know, where we start. Okay. When it comes to moment of inertia of composite shapes, okay, which is what this is, the types of problems you have are of two. One, you are given an XY axis and you are asked to find moment of inertia about those axes. That's one type of a problem. The second type, this is the easier one, easier in terms of less operations involved. Or you're asked to find moment of inertia about centroidal axes. Okay? That means you need to locate the centroid of this shape, set up an axis, okay? And then find the moment of inertia of this shape about this axis. So you need to do the calculation to locate the centroid first, and then draw this axis and do all your measurements from this. So to begin with, I will first do a problem that is dealing with the moment of inertia about a given set of axes, which is this problem, okay? And I will demonstrate that how it is done, okay? I hope I have at least time to set up the essential parts, okay? So type 1, moment of inertia about X and Y, okay? So to start with, what do you do? Similar to the way you did Centroid. So step number 1, divide the shape into sub areas. Okay, so this is what I would do. I would consider this little circle as a one area. Okay. I call that A1. This is A1. Remember, that was negative, so I label it like that. I consider this part that is cut out as A3, A2, I have considered that as this one. So A1, A2, A3, all these negative areas, and then A4 will be this rectangle or square that I had here. So this is A4, okay? So that's a step number 1. So at least we could finish the step number 1, but let me also start, at least give you the introduction to the second step. So you set up a table similar to what you did, okay? For Centroid. In fact, if you are asked to find the moment of inertia of this shape about this centroidal axis, the first part of that table will be the same, okay? So this is what you do, okay? 1, 2, 3, and 4. These were the areas. So you have A1, A2, A3, all negative, and A4 positive, okay? And you tabulate these areas. And I'm going to stop here and pick it up from here for next time, okay? All right. Have a great weekend, and I may see you during my office hours. I will start my office hours at 11:45 today. And I will also talk about the arrangement for, send you an email about the arrangement for DRCs that I've made it a much easier, better arrangement next time. All right. If I don't see you, have a great weekend and enjoy it. Thank you.
Thank you.
Thank you.
Thank you, Professor.
Thank you.